f double prime of 0 then is positive 2. You're going to see a pattern start to emerge here. We talked about that last time. When you see these patterns, you're going to end up doing a lot of these a lot quicker. -3 times 2 is -6 times 1 minus x to the -4. Once again, multiply by a -1 because the chain rule. All these end up coming out positive, so we're seeing that pattern. And you might start to notice the other pattern. Notice what's happening. The exponent's coming down and multiplying by that next number. So we'll do the fourth, but I think once you see the pattern, you actually don't even need to take the derivatives anymore. -24, 1 minus x to the -5 times a -1 because the chain rule makes that positive. So fourth derivative is 24. The next one's going to be times 5, so it's 120, so on and so forth. And, if we want to, we could say, well, remember, 6 is 3 factorial, 4 is 4 factorial, the next one will be 5 factorial, so on and so forth. All right, let's get back to what we're looking at here, which is first thing we need the Taylor series. So we need our Taylor coefficients. Our first term is 1. And then we get our next one, which is 1. This is centered at 0, so times x to the first. If it was centered someplace else, we would put x minus in parentheses. Plus our next term is going to be 2 over 2 factorial x squared. Our next term is going to be 6 over 3 factorial x cubed. And then because we're asked for a 4th degree, we need something raised to the 4th power, so we need the next term. So 24 over 4 factorial x to the 4th. Now, we're going to simplify this as much as possible to see what this looks like. So we have 1 plus x, and then 2 over 2 factorial, that's just 1, those cancel. So plus x squared, 3 over 3 factorial, well, those cancel, 3 factorial is 6, so it's just x cubed. And we see this pattern emerge really quickly. All right, so this is the 4th degree Taylor polynomial. And if we want to maybe give that a name, p sub 4 of x. That's our 4th degree Taylor polynomial for the given function centered about 0. Again, this is going to start off as a little bit of review, but if you have questions, let me know. These terms would just keep going like this infinitely. So to write this thing in summation notation, we have the sum of, this is actually not a bad one, right? It's just basically going to be x to the n if we start at 0, because that'll make x to the 0, which is 1. Started at 0 up to infinity. So that's going to be the Taylor series of 1 over 1 minus x. Now, we want it in this closed form so we can do the interval of convergence. As we saw last time, the interval of convergence basically means we want to apply our ratio test. So we want to apply our ratio test here. So we have the limit as n goes to infinity, a very easy one to set up. X to the n plus 1 over 1 times the reciprocal n plus 1, I said it but didn't write it, times 1 over x to the n, the absolute value. Now we know from our canceling, this becomes limit as n goes to infinity of basically just the absolute value of x, which is actually equal to the absolute value of x. Because there's no n. So basically it's like having the limit of n goes to infinity of 1. And we know this converges if this is less than 1. So right off the bat, our radius of convergence is 1. Now, to do the interval, we have to check the endpoints. This is what we were working on last time. So we know that x is in between 1 and -1, so those are our two endpoints. So if we check our endpoints, so first off, we check 1. Well, then our series becomes 1 to the n, or just the summation of 1, which goes to infinity. So this diverges because the sequence does not go to 0. We could call it our divergence test. So by our divergence test. Similarly, even if x is -1, we have -1 to the n. That literally just flips back and forth between 1 and 0. So that actually does not have a sum either. And we could use the same argument that sequence does not go to 0. It's also divergent by the divergence test. So we don't want to include either endpoint. So our interval of convergence is -1 to 1. We can put this in interval notation if we want, but we don't want to include -1 or 1. Now, there's a couple reasons that I specifically picked this series. Number one, let's write this out so we can kind of see what's going on. The series of x to the n equals 0 to infinity is equal to 1 over 1 minus x. Well, we've encountered this before when x was our common ratio. So if we think of this is an exponential function, so this is basically geometric. Remember, the sum of an infinite geometric series with a common ratio of r is equal to the first term over 1 minus the common ratio if that common ratio is the absolute value of it is less than 1. Again, exactly what we found here. We actually did this in the reverse. So back in section 8.2, in the lesson, this formula was derived for the sum of an infinite geometric series. Now what we're doing is we're taking the formula of the infinite geometric series, using Taylor series, or finding its Taylor series to show that it is the sum of an infinite geometric. So part of the reason I chose this one is I love making that connection because it's something we've seen before. We're just now doing it in the reverse. The other reason that I like that we're using this one is we're going to modify this and see how we can use a known Taylor series to find more complicated Taylor series. But before we go into that, any questions about this first one? Okay, we need that foundation to go and do some of the other stuff we're going to do. Now, let's talk about using a known Taylor series to find a more complicated Taylor series. So as you just saw, to find the Taylor series, we had to take a bunch of derivatives. This one wasn't that bad. It did involve chain rule, but really not a bad chain rule. But what if our function was something like a polynomial times a trig function? All right, first derivative needs product rule. Well, these derivatives get increasingly more complex because of the need for chain rule. So if we wanted to find 6 or 7 terms, this could be a lot of work. But we can use what we already know. We know the Taylor series for sine of x. So the Taylor series for x squared times sine of x, we just multiply all the terms by an x squared. So what's happening here, and I just want to make it real obvious, and let me know if you have any questions about this, but what's happening, Notice all the terms now have an exponent that's exactly 2 higher. So what we did is we took this guy and we multiplied it by x squared. Well, what did that do? That increased all the exponents by 2. So in the closed form, our exponent is now exactly 2 higher. We did not have to take a single derivative of x squared times sine of x. Okay, this is what's called using a known Taylor series to find more Taylor series of more complicated functions. Now that we have the Taylor series for this guy, we will look at a more complicated version. But before I go on, any questions about this idea? Okay, then let's see how this plays out. So let's see, we're going to want more rooms. Let's go to a new slide and just write down what we know. Okay, so what we learned in that first slide that we're going to bring over. Here's what we already know. We know that 1 over 1 minus x is equal to the Taylor series from n equals 0 to infinity of x to the n, right? That's what we saw last time. And if we wanted to write that out, it's 1 plus x squared plus dot, dot, dot. Now we're going to look at the middle one because that's the one that's set up for the one we're working on. Now, I showed you how it works for multiplication. I'm going to show you how it works with a composition. All right. So I'm going to do this in a couple of different steps, and I'll use different colors to identify. And the first thing we're going to do is we're going to take care of the 1 plus x cubed. How do we make this look like that? Well, here's how we do it. So 1 over 1 minus a negative x cubed. That's equal to 1 over 1 plus x cubed. But the way it relates to the first one is we have a composition. All the x's are getting replaced with a negative x cubed. Let's do it in this form first, and then I probably should have written these the other way. So 1 plus negative x cubed plus negative x cubed squared plus negative x cubed to the 4th. I think that's plenty of terms. Excuse me, to the 1st, 2nd, 3rd. Skipped one. I think that'll be enough terms for us to see. If we need more, we can always put them in. And then we got to figure out, okay, well, then there's the summation. All right, well, n equals 0 to infinity of negative x cubed to the n. All right, I want to simplify what's going on here because I want you to see something. So we have 1. Now it's negative when the exponent is negative. So 1 minus x cubed. This one is going to be plus x to the 6th minus x to the 9th. You can probably start to see the pattern, plus x to the 12th, so on and so forth. All right, now we want this summation notation to match up. It's all in here, but we're going to make it look a little cleaner. Right off the bat, we see that it's alternating. So I'm going to split off the alternating piece the way we're used to seeing it. Negative 1 to the n. So I'm just taking that negative and raising it to the n. And then x to the 3 to the n will be rewritten x to the 3n. And we can see that, okay, the alternating plus, minus, plus, minus, plus. Okay, that works. And x to the 3n, when n is 0, we get 1. When n is 1, we get x cubed. When n is 2, we get x to the 6th. So we have now found the Taylor expansion for, let's write it this way, 1 over 1 plus x cubed. So we've taken care of how we make the denominator do that, and we do it via composition. Questions at this point? All right, well, we were asked to find x over 1 plus x cubed. Well, basically, we're thinking of it as x times 1 over 1 plus x cubed. So everything's getting multiplied by x. So 1 minus x cubed plus x to the 6th minus x to the 9th plus x to the 12th, dot, dot, dot. And then this is getting multiplied by an x. So negative 1 to the n, x to the 3n, and then times that x. So we wanted the Taylor's expansion for x over 1 plus x cubed. We're going to just basically distribute that x to all these terms, which it really just raises the exponent by 1. So x minus x to the 4th plus x to the 7th minus x to the 10th plus x to the 13th, so on and so forth. And then for our summation, we have negative 1 to the n. We can combine those because they have the same base. That would be x to the 3n plus 1 up in the exponent. Still going to start at 0, still going to go up to infinity. And what we've done is we found the Taylor expansion for this function without having to use quotient rule and product rule and chain rule to take the derivatives. That is what's known as using known Taylor series to find other Taylor series. Saves a lot of time on some of these more complex functions. You'll get to practice a couple of these in the homework, where you're taking a known Taylor series and using it to derive another one. Okay. Questions about this? So we found this Taylor series using a composition and also using multiplication. So those are a couple methods of taking a known Taylor series and using it to find a more complex Taylor series. We'll look at a couple other ways. We can do that right now. We might come back to that to let you guys try some. We can also do this via integration or differentiation. So we know that the derivative of 1 over 1 minus x is 1 over 1 minus x, the quantity squared. So if we want to find its Taylor series, we want to do the derivative of the Taylor series for 1 over 1 minus x. So 1 plus x squared plus x cubed plus dot, dot, dot. Very similar. We just take the derivative term by term. So we end up with 0 plus 1 plus 2x plus 3x squared. Next one will be 4x cubed plus dot, dot, dot. And then for summation notation, very similar also. It was x to the n. We take the derivative with our power rule, n times x to the n minus 1. Now here, because now we can actually still, yes, we can still start this at 0, because plugging in 0 is 0, that works. Plugging in 1 would give us 1 times x to the 0, which is 1. Plugging in 2 gives us 2 times x to the first, so on and so forth. Now, I won't bore you with this one, but this one, we're trying to do ln of 1 minus x. And we know that the derivative of ln of 1 minus x is negative 1 over 1 minus x. So this is the one where we need the antiderivative. So here's what we know. Negative, I'm going to write it this way, ln of 1 minus x is equal to the antiderivative of 1 over 1 minus x dx. And this is 1 plus x squared plus x cubed plus dot, dot, dot dx. And this is going to look really similar to what we did before. So we're going to have x plus x squared over 2 plus x cubed over 3 dot, dot, dot. And that, as we saw before, gives us x to the n plus 1 over n plus 1 from n equals 0 to infinity. None of that has changed. Here's what's going to be a little bit different. This is the Taylor expansion for negative ln of 1 minus x, this negative sign here. So if we want it for positive, so if we want the Taylor expansion for ln of 1 minus x, we have to multiply all the terms by a negative. So minus x squared over 2 minus x cubed over 3 minus dot, dot, dot. And then we need to put a negative on our summation. And I'm just going to throw it out front. I think that's as easy as any place. X to the n plus 1 over n plus 1. And the limits stay the same. What I wanted you to see with this is how we can use derivatives or antiderivatives to use a known Taylor series to find another one. And these methods can be combined. You could use an antiderivative to find one, and then if you had to multiply by a, like if we wanted to find, say, if we wanted to find x cubed ln of 1 minus x, we would take what we found here and multiply it by x cubed. So all these methods can be combined. And the reason I want to show you all of these is not because we're going to do a ton of them. We'll do a few, and it's really usually pretty obvious. If the derivatives look like they're going to get really messy really quick, what you want to look for is, hey, is this a multiple or a composition or a derivative or an antiderivative of one of our basic ones? Is it a cosine of x is a basic one, sine of x basic one, e to the x is a basic one, 1 over 1 minus x is a basic one. There's some basic Taylor polynomial expansions that are easy to find and we use often. And those ones are the ones that we look to use to see if we can find Taylor expansions for some of these more complicated ones. Because Taylor series and Taylor polynomials are an approximation, we always want to know how accurate they are. So just like we had with our numerical integration, we have an error estimation. This is going to look really familiar. So our error estimation for Taylor polynomials for the first nth degree is given by what's called Taylor's inequality. This will look really familiar. This is what is used to derive those error formulas that we use for the midpoint rule and Simpson's rule and trapezoid rule back in our numerical integration section. This is exactly where it comes from. So you're actually doing a lot of the same stuff. So what I want to work on is how we use this in practice. Okay. So let's go ahead and take a look at this one. This one's not too bad. It won't, but it'll get us just kind of used to the error. So if we wanted the error in the 5th degree Taylor polynomial centered at a equals 0 for f of x equals sine x, when x is in between negative 0.5 and 0.5, we can use that approximation. So we want a 5th degree for sine x. We don't have to, for this one, we don't actually have to find it. We certainly could, because we know that this is one of our basic Taylor series centered about 0, but we don't need it. So here's the way that this works. So we know that we're in between negative 0.5 and 0.5. We're in the 5th degree. And I want to bring that error back up. That's why I'm writing this stuff down. So we're looking at the 5th degree Taylor polynomial. And we know that the absolute is centered at 0 is less than or equal to 0.5. You're going to see a lot of the stuff is going to pull right out of there. So if I go back to our term, it's m over n plus 1 factorial times x minus a to the n plus 1, as long as x minus a is less than d. Okay, so the d is this 0.5. This here is our D. And you'll see, and I'll show you why that's important. Now, here's what we need. We need M. This is where all the work is done, just like it was back in those take-home problems for the midterm. Well, the thing about sine is its derivatives are all either sine or cosine, positive or negative. So we know that we have to bound the sixth degree derivative, we know that the sixth derivative is always going to be less than or equal to 1. So we're going to use that for our M. So here's how this works. And it's a fifth degree. So our N is 5, just to get you used to how all these pieces work. So we know that our error in the fifth degree Taylor polynomial is going to be less than or equal to 1 over 6 factorial, that's the n plus 1, times the absolute value of x to the 6th. So the question is, okay, well, what about this part? That's where this comes in. This is saying the absolute value of x is less than or equal to 0.5. So what we're going to do is replace the absolute value of x with 0.5. So we get 1 over 6 factorial times 0.5 to the 6th. That is going to give us our error estimation. So if we want to, that's something if we want the, we might need the number, we might want to do a comparison. This is something we can do in the calculator. So if you're not sure where the factorial is, let's go through that now. You go under math, it's going to be under probability, and there's your exclamation point. So there's our 1 over 6 factorial, and then times 0.5 raised to the 6th. So a really small number, and it's because we have such a high degree polynomial and such a small interval. So this is what, 2.17 times 10 to the negative 5th, or if we wanted to write it not in scientific notation, 0.21, excuse me, not enough zeros, 0.0000217, and then however many digits we need for our problem. So it's going to be a really small error, and it's because we're on such a small interval for having such a high power of polynomial, Taylor polynomial. Again, guys, you have dealt with this error estimation stuff before, and it's very similar. There's only a couple of small differences. But questions so far. So the n is the degree. M is what we need to calculate. X minus a is basically going to be given in our problem. And we're going to do another example here in a second, but I want to see if there were questions about this one first. Okay. So we'll come back to this, but here's what I want to look at is this example here. All right, this is going to be some of the stuff we did earlier, and then some of the stuff we did on Thursday, some of the stuff we did earlier today, and this is going to be what you need to know for the first take-home problem for the final, which, as we talked about last time, is now available. All right, let's see what we're asked to do. F of x is ln of 1 plus x, and we want to approximate ln of 1.5. Now, ln of 1.5 can be done in any calculator, so we know the exact value. What we want to do is figure out what the maximum possible error is, calculate the actual error, and see how far off we are using a third degree Taylor polynomial. So we're going to need the third degree Taylor polynomial for this, which means we're going to need at least the third, we're going to need up to the third derivative. Actually, I don't think I have this set up. Give me just a sec. Let's put that off to the side. Our goal is to approximate ln of 1.5. Okay, so first off, something we've done before, the third degree Taylor polynomial. That we should be getting better at this point. So f of 0, ln of 1 is 0, f of 0 is 0. So now we start finding derivatives. F prime is 1 over 1 plus x. And this may be easier to do written as 1 plus x to the minus 1. All right, because that right there, we know that our f prime of 0 is just 1, because 1 to the negative 1 is 1. But this is going to make it easier to find our derivatives. F double prime is negative 1 plus x to the negative 2. And f double prime of 0 then is negative 1. We can already probably start to see, okay, it looks like we might have an alternating series here, but let's check it out. F triple prime of x, we're going to need this one for the third degree Taylor. Negative 2 times negative 1 is a positive 2. 1 plus x to the negative 3. F triple prime of 0 is going to be 2. And we are going to go one more because we're going to need it for the error term because we need the n plus first. Well, that gives us negative 6 times 1 plus x to the negative 4th. And f, the fourth derivative at 0 is negative 6. We now have enough to build our third degree Taylor polynomial. So our third degree, this is exactly what we were doing before. I'm going to write it out and then we'll simplify it. So 0, we're going to center this at 0. It didn't say in the problem, but we're going to want to center it at 0 because we're just estimating ln of 1.5. So we're centered at 0. So 1 times x to the first minus 1 over 2 factorial x to the second plus 2 over 3 factorial x to the third. We're done. That's a third degree Taylor polynomial. Remember, this extra term was for when we go to look at the error. So let's clean this up a little bit. We don't need the 0. We don't need the 1s. So we have x. 2 factorial is 2. So minus x squared over 2. 3 factorial is 6, but 2 over 6 is 1/3. And I probably don't even need to go any further. You probably, if we needed more terms, I bet you could figure out the pattern on this one. But we were asked for a third degree Taylor polynomial, and that's what we got. Okay, so there's the third degree Taylor polynomial. Now, let's talk about calculating the error. Now, this is pretty interesting. So our function is ln of 1 plus x. So ln of 1.5 is actually our function evaluated at 0.5. Okay, because putting 0.5 in will give us that. So that's one of the things you got to be careful of. I don't want to put 1.5 in here because then I'm calculating ln of 1.5. So when I go to find my approximation, I'm basically going to be putting in 0.5 into my Taylor polynomial. Now, here's why that's important. Let's go back to our error term so you guys can see it. It's important for right here. X minus a has to be less than or equal to d. So our d is going to be 0.5. So we get the absolute value of x is less than or equal to 0.5. Now, the last thing we have to do is we have to maximize the n plus first derivative on this interval. If the absolute value of x is less than or equal to 0.5, we're actually on the interval. from negative 0.5 up to 0.5. Now we'll also look at 0 on this one because something interesting is going to happen there, but I want to do it on the full interval first, and then we'll look on the half interval because I want to show you something. Okay, now remember we have to optimize this function. Optimizing a function, it's on a closed bounded interval, which we're on, happens at one of two places, either at an endpoint or at a critical point. We can take the fifth derivative, but our only critical point is going to be at -1 because that's the only thing that makes this actually discontinuous. It doesn't even make the derivative 0. -1's not in our interval. So what we're going to do is calculate our fourth derivative at -0.5, which comes out to be, I believe, 90, let's see. Can't read my own handwriting. So remember what we're doing. We're plugging this into the fourth derivative. So we have -6. Actually, we don't care about the positive or negative. So because we want the absolute, the biggest magnitude, 1 minus 0.5 raised to the -4. 96. Okay. I couldn't tell if I wrote 90 or 96, so I wanted to check. So that's 96. All right, we'll also do our derivative at 0.5. Same thing, you're plugging 0.5 into here. And for this, you get, as a fraction, you get 32 over 27. If you want it as a decimal, it's 1.185, and those terms are going to repeat. Okay, so clearly this is going to be our M. So our error estimation for the third degree Taylor polynomial, we know that the error in our third degree Taylor polynomial is going to be less than or equal to our M, which is going to be 96 over 4 factorial. Now the x minus a, well, x minus 0 is going to be the 0.5. And then to the 4. These numbers are always going to match. If you calculate that, we actually get a pretty big number on this one because of the -0.5, which is 0.234375. Pretty big. So there's a lot of wiggle room on this one. So now what we want to do is we want to make sure our error works, our error estimate works, because we can find the exact value. So what we're going to do is we're going to take the value from our third degree Taylor polynomial, and we're going to subtract off the actual value, ln of 1.5. Because we're looking at errors, we just take the absolute value of this. Now, the way this is computed, you're just putting 0.5 into x here. You can use a calculator or Wolfram or something to calculate that. And we'll subtract off the ln of 1.5. And we get a considerably smaller error than our estimate, 0.0112015586, which is definitely less than 0.234375. Okay, again, it's a very conservative error estimate. Now, one of the things that, oh, actually, before I go on, any questions about this one? About any of the parts? Like I said, you guys have actually had practice at this because you did something very similar for the take-home problem on the midterm. Again, the error formula is derived from this Taylor inequality. So you're really doing a very similar procedure. Now, one thing that I like to show on this one, and it happens on a lot of these, because this thing is centered at 0, we could have actually, let's do some different colors just to make it obvious that it's not part of this one. We could have done it on the interval from 0 to 0.5. This is a little bit less conservative, but because of the type of function we have it and we're all the way out at the endpoint, we could actually do it on this interval. I want to show you guys both ways. This is the way off of the definition, but a lot of times when you're only dealing with like half of the function, you can go from where you're centered out to where you're interested at. Now, the only change that this makes is instead of checking this one, we do our 4th degree at 0, which is really easy to calculate, which is 6, and we would use that for our m. So in this case, e sub 3 would have to be less than 6 over 4 factorial times 0.5 to the 4th, excuse me, space down. Lost my place there. Keep hitting the wrong thing there. To the 4th. And this comes out to be 0.015625, which is still greater than our actual error. Zero 15625. So again, a lot of times with these, especially with these ones centered at 0, we can actually do this because this is actually the side of it that we're interested in. So this will work. But if we go off of the definition, this is the interval that we'd want to use. It's more conservative. And that's why we got a much bigger m for that. So again, the reason I wanted to go through this with you, these are going to be the kind of things that you're going to do in the take-home problem. You know, you're going to be finding a certain degree polynomial, using it to estimate a value, looking at the actual error versus the estimated error, making sure that your actual is less than your estimated. Very similar to what you did in the take-home problem on the midterm. So I want to make sure we went through one of those together.